Hi, my name's Tim Place, and I'm one of the engineers at Cycling 74. And I thought I'd share with you one of the hidden features of Max 7 that you might have missed in all the excitement over all the other sort of front burner cool things in there. So one of those things is JavaScript access to the buffer object. And I thought I would demonstrate it by just creating a little patch that uses it, that you could use as a basis of doing something of your own invention. So let's do an analysis patcher of a buffer. Analysis may not sound super interesting, but what you could do with that is do something like create automated like warp markers or something like that. So if you just drag in a sound file from the side there, you can get this playlist object and play it, and that's all great. But there's another little trick here where if you hold down the Option key on the Mac or the Alt key on Windows and drag out your sound file, then you can create a different sort of object, like an SF play, or in this case, we're going to work with a buffer object. So this makes a buffer object for me with this brushes sample in it. I'm going to change the name of this buffer object, but not the name of the sound file that it takes. So we can look and see it still is that same brushes sample. I just named it foo because I have this little patch down here which already uses foo. And this patch should be somewhat familiar if you've used buffers. The play object is going to play the samples back given an index into that which is in milliseconds. So we can use the info object to find out the size of the buffer and set the frequency of our phaser and the scaling of that signal in order to drive that. So I'll just go ahead and do that now. And now we should be able to just play the sound file. Okay, so that's great. So we have our buffer object. To make things a little easier to understand, it's always helpful to visualize the data you're working with. So I'm going to go ahead and instead of using the waveform object, which is sort of the default people use because it has been around longer, I'm going to use a plot object. And to use a plot object, for this case, we'll just set it up for a waveform display for the buffer object. Then we can come here and we can tell it that we're going to refer to the buffer called foo. Great. So we can see what that looks like. So let's jump in now to doing something with JavaScript to access the contents of this buffer named foo. So I'm going to make a new JS object, and I'm going to call this bufferlove.js. So we'll go ahead, we can open up the JavaScript editor window, and now we need to type some magic into this window in order to use the JavaScript access to buffer. If we imagine for a moment that I don't know what to do, I can open up the buffer help patcher, and there is a tab in the buffer help patcher which demonstrates some of the different features that you can use here. So as an example, here's one that's going to post 10 samples to the Max window. Here's one that gives you some of the metadata about the buffer. And here's an example that's going to fill it with a ramp. So that's all handy. I can look in here and see that the type of buffer syntax I need in order to create this would be to have a variable and create a new buffer object. And the argument is going to be the name of the buffer itself. I'll just go ahead and copy and paste that right now to get started here with bufferlove. Then I'm going to go ahead and make a function. And I'm typing with mittens on in case you didn't notice. I'll call this function bang, and we'll probably just do everything we want to do in our function bang. Oh, we ought to make sure that we get the buffer we want, foo. And just so that I don't go crazy, I'm going to call the variable foo that references the buffer named foo. That'll be kind of a nice deal. So given I have this buffer named foo, what exactly do I want to do with that? Well, what I'm going to do in this case is I'm going to go ahead and do an analysis of this that shows me where the big attack transients or the big events are in this buffer. So to do that, a typical way of doing that is to get an RMS envelope of this sample. So we can do that, and then we'll stuff that into another buffer that will represent that envelope. So if that's our first step, then we need to make another buffer to represent the envelope. Buffer env. How long do I make it? I don't know. I want it to be the same length as the other one. So we'll do that in the JavaScript. Here we are. And we'll go ahead and we'll make a buffer object for this as well. Buffer env. Okay, so our first step then is that we need to know how long the existing buffer called foo is. We can do that with the length message. Now, if we imagine that I didn't know that there was a length message, I could go hunting through that help patcher. Or if we went to the documentation window and we do a search, I can do a search for JS buffer. JS buffer is the internal name for this. And we can see that there's a guide for the buffer object. And this guide for the thing called the buffer object, this is the JavaScript guide. And it will tell us, for example, that there's a message called length. And it'll return the length of the buffer in milliseconds. So that's handy to pull this up if you're going to be using this. So now we can address the env buffer. We'll address it, we'll use the send method. What the send method does is it lets you send any message to the buffer object that you could send in via an inlet. So if we came to a buffer object and we looked at the messages, we can send all this stuff, crop or normalize, fill, etc. In this particular case, we need to send the set size message and then the number of milliseconds long to make it. So now that buffer will be set up for us. And now what we'll do is we'll do the RMS. So we'll start by iterating through each sample of the buffer. So we're going to say I is going to be our index as long as that index is less than the total number of samples that are in the buffer. The total number of samples is going to be what's known as the frame count. And then we're going to increment our index. Okay, so what is it that we need to do for each sample? Well, RMS is root mean squared, and so we're going to start off, we'll start off by getting our source sample, and that we can do with the peek method. And so the peek method, the first argument is the channel number, which is a 1-based channel number, so that's the first channel. I, which is going to be the 0-based index or frame. And then the number of samples we want to fetch. We can fetch samples in bulk, which is dramatically faster than the way we're doing this right now, but the way we're doing this right now will be a little bit easier to understand. Okay, so we're just going to fetch one sample. So there's our source sample. So the first thing we're going to do is we're going to square the value. So we're going to say squared, and it's going to equal this times itself. Then we need to get the mean. We're not really going to get the mean, we're just going to approximate it using a recursive low-pass filter. And then, and we'll come back to that. And then we need to take the square root of that. So we do that, we get math.square root of the mean. Okay, so for this low pass filter that we're going to implement, it's just going to be quick and dirty. We're going to have a variable to represent the feedback coefficient. And the feedback coefficient, we could adjust this or make it a parameter. I'm just going to make up a number that should pretty well work. And then we're going to need something to keep track of the feedback sample. This would be a one-pole low-pass filter. And then we can come down here, and what we'll do is we're going to take the feedback sample times the feedback coefficient, go figure. And that gets added to our input. The input to this filter is going to be the squared sample value. And that's going to be multiplied by what's left of 1, basically, from this feedback coefficient. So we're going to say 1 minus feedback. Better copy and paste it, because otherwise I'll make a typo. Okay. So there's our RMS envelope. Okay, so what we're going to do now is we're going to take the env buffer and we're going to poke this value into it. 1i first channel, whatever sample value we're calculating, and then this is the value that we're going to pump into there. Okay, and then in order for this filter to work, we need to store the feedback sample. Whoop. Feedback sample. No feedback sample. That. Okay. So we're going to save this. It's going to ask us to save it somewhere. And I'm going to go to my documents folder. I'll just stick it in this library spot. Okay. So we can do all of this. And now if I come back here, we'll make another one of these guys that'll work for the buffer called env. And then we'll send a bang to our little analysis guy here. And look at that. We get basically the envelope of our percussion sample here. So that's cool. This is still not like super smooth. There's a couple ways we could try to smooth that out. We could increase the filter coefficient, or another thing that works really well is sometimes you just do like another RMS calculation on the whole thing. And for our case right now, that's going to be like an easy thing that we can do. So I'll go ahead and do that here. So I just copy and pasted it. We could make another function for it or something, but we won't bother right now. And then we need to make sure that we're using the correct input. So our source sample isn't going to be foo. Our source sample is going to be the env buffer. The rest of this should be able to be the same, except that we need to reset our feedback sample. Okay. So now I'll save that, close it, and hit our button, and we should see that this is smoothed out even more. So that's great. This is certainly something that we could work with depending on what we wanted to do with it. What I'm really wanting to do is I want to find out exactly where each of these attacks are, and then do something with like that specific location. So I'm going to create another buffer for our analysis, another stage. I'm going to call this delta. And then we'll go ahead and we can drop this guy down here. delta. Of course, there's nothing in there yet. Then we'll come back to our JavaScript and we'll do another pass on this whole thing. So what I'm going to do with the deltas is the idea is I can go through each sample of this and compare it to the sample before it. And in that way I can see, is the sample going up or down or whatever. So first thing I need to do is I need to set up this delta buffer, similar to what we did with the omp buffer. So I'm going to set up the delta buffer. I'm going to go ahead and add just a couple comments in here too. Here's Rms Envelope, analysis. Now we're going to our delta analysis. Okay, so we're going to go to this delta buffer and we're going to send it the set size. Oh, but we need the delta buffer. So go ahead and the delta. Okay, we can come here now and we're going to have another for loop. Okay, so we're going to have a variable I'm going to call diff. Okay, and this is going to be the difference between the current sample and the previous sample. If we're at the first sample, then it doesn't count. So we're going to say diff equals 0. Otherwise, we can go ahead and do the math and say that diff is going to equal, and we're going to use the omp buffer. We'll use this peak method and say channel 1, whatever the current sample is that we're working our way through. We're just getting one sample. Take that minus the previous one, which would be I minus 1. Okay. And then we're going to go ahead and poke the results into this delta buffer on channel 1, our current index. We're just puffing. Here's the sample value that we want. So we can do this, and we're going to see when we come over here is not very impressive because it just looks like a line. The values are really small. So what we want to do is we want to normalize these values so they're in a range of 0 to 1. So we can go ahead and incorporate some normalization into this loop. I'll do that by making a variable called max. It'll start off at 0. And then when we get to the, when we go through here, we can say if the diff is greater than whatever the current maximum is, we'll go ahead and assign the new maximum to be equal to diff. Okay, and then we'll do yet another for loop where we can apply that normalization. So var scale, and that's going to be 1.0 over that max variable. Let's say you have to go through the whole thing all over again. It's just like what we've done before. I'll just copy this thing. Now, if you're thinking all these for loops are really inefficient, that we're doing a whole bunch of them like this, then you would be correct. And it'd be much more optimized if we just did this all in one for loop. But I'll leave that as an exercise for the viewer. Okay, delta poke, first channel, current index, and then it's going to be delta dot peak 1 I1 times whatever that scaling factor is. Okay, so that should give us normalized version of this delta. Now we can go here, run our buffer love, and sure enough, now we get some really prominent peaks where these events are in the buffer. Awesome. Now we need to boil this down into like a list of numbers that would show us, say, these 4 peaks. So to do that, we can add like a little threshold analysis here. It's not maybe quite as easy as it looks at first. If we look at this, it just looks like, oh, there's a sample here and here and here. But the reality is that there's like a whole slew, like maybe hundreds of samples across where this is high. And then, there's little bumps here. So we have to do a couple of tricks with our threshold analysis. Okay, but the first thing is we need to define a threshold. This threshold, again, this is like a parameter that you might want to make adjustable. I'll leave that also as an exercise. Also, we're going to need a place to store all of the events or attacks that we detect. So I'm going to make a new JavaScript array. Okay, continuing with the theme, we're going to have another for loop. I'll just copy and paste this for loop, and then we'll yank out the contents of it. Okay, so here's what we're going to do. We're going to have a value, which we're going to fetch out of there. Again, delta peak, first channel, current sample, 1 sample. Okay, so we have a value. Now we're going to say if that value is greater than the threshold, then we're going to push it onto this array. So that array is called attacks. We can use push, that's standard JavaScript. So searching for reference on the array, if you aren't familiar with this, you can look up the push method of the array with your friend Google. And we're going to push the, we'll push the sample index on there so we know where it happens. And otherwise, at the moment, we won't do anything. And then when we're all done with our bang method, we'll send that list out our outlet. So this will return everything that's above 0.5, which is going to be like roughly right here. Should give us 4 events. But these events are going to be like, it could be hundreds of samples, and it's not going to be actually all that useful to us. So what I'm going to do is I'm going to add a hysteresis to this threshold function. And the hysteresis says that basically like an attack can't happen until the signal has gone back down below another threshold. I'm going to say var hysteresis. So I'm going to say that it has to drop back below 0.25. Again, this is a little bit arbitrary. I can see that it's going to work with this file. You might need to adjust that some, or even make it something that you can change on the fly. But I'm going to set that there. And then also I'm going to need to know if it's been triggered or not, so that I know whether or not I'm looking for the hysteresis. So I'll have a var here called triggered, we'll say, and set it to false. Okay, so now we come down here. How's this going to work? Well, if we've pushed an attack, then triggered should be true. And if an attack has already been triggered, then we don't want to push another value. So we're going to say triggered must be equal to false in order for this to happen. And so then we can just else if the value is less than the hysteresis, then we can reset that triggered Boolean. Okay, so the chances of me having a typo in here are really high, but we'll just give it a shot. And I need to hook it up if we're going to see if it worked. Oh, brilliant. Okay. I somehow managed to not have a typo. That's awesome. Okay, so now we know that at sample number 132, we have a spike. At sample number 103,000, I mean, so that's kind of crazy that we're working in those values. We ought to go ahead and use the sample rate to get these numbers into milliseconds. So I'm just going to use a quick little vexpr object and say that we have these integers. We're going to divide them by the sample rate. I could get the sample rate from over here. I'm just going to be lazy right now. Don't do this. Do as I say, not as I do. Scalar mode. 1 means that I'm going to do this like division on each of those items. Okay, so we do that. Actually, we'll go ahead and move. There we go. That's what I was trying to do. Okay, and then vexpr. So it should be, we do this. Now you might notice, okay, it does take a little bit of time because of the way we structured that JavaScript, and it needs to be optimized, but okay. These guys shoved over here. Okay, so here's the offsets now. This is the wrong calculation because we're working in milliseconds, not in seconds. That looks much more reasonable to me. Unjoin, we know there's 4 of them. So if we use unjoin, which is, it's like unpack, except I don't have to type a billion arguments. I just tell it how many outlets I want. I'm going to hook this up to trigger something to happen at each of these spots. So one way I can do that is I can go ahead and use a greater than tilde object. So if this, if we hook the input up to this, which is the millisecond index into the buffer that's playing back, if we hook that up and we say, you know, if is the index greater than whatever this sample value is here, then we can hook that up to, whoops, hook that up to an edge object. Then we hook the edge object up to a toggle object. You just do that. We'll just do it for the first 3. How's that sound? Let's go ahead and we'll just use it to like add some hi-hat or something like that to this little symphony we have going on here. Probably those are smaller. Okay, this one will work. Sim. And again, I'll option drag it in here, create a buffer with it. I'm going to call it something different in case I want to change it to be not a symbol. Double check that it's got what I think it has. It does. Then I can use a play object with the accent. And the play object, you can hook it up. This is the old school way of hooking up a play object where you're driving it with an index, but you can also just hook a toggle straight up to it. As of Mac 6 or 7, I don't remember exactly which. So now we have these 3 symbols playing, and I can go ahead and hook them up like that. And we'll play it back. There's probably one more thing we're going to want to do to this, but we'll just try this as it is first. Okay, so it's playing them back. They're all locked in right with our rhythm. It's I'm not sure how picky I'm being, but one thing, this is a little bit delayed sounding, and so that's going to happen with this type of analysis. These edges can get rolled over, and then this symbol has like a little bit of a slowish attack transient as well. So to really make this sound satisfactory, a lot of times it's helpful to do a little bit of latency compensation to it. So I'll do some Vexper action again on our list, and in this case we're going to have floating point inputs, and this is not very scientific approach to this problem, but just from experience I know that if I'm shooting from the hip, starting with 10 milliseconds is usually a good place to start if I want to do some sort of latency compensation on this type of processing. So I'll go ahead and start her up again. Actually, I'll do our buffer analysis again. It'll run. Okay, so the first attack, because we are subtracting 10 from this, it's ending up being below 0, which means that this greater than comparison is always failing. So we should do some sort of like, in the case of this first sample, we should do some sort of like clip 0.01 or something silly like that. It's kind of a hack, but that's all right.